And now what we want to do is do the comparison. We want to compare to 3 CSTRs in series. Okay, so let's draw out what this situation might be. Again, if you ever have a problem like this where you're comparing two things, you should draw both of those systems. So we've got, we're going to assume here that these 3 CSTRs are of equivalent volume. So we're not trying to play around with the volume of each of these tanks. We're just imagining 3 equal tanks. So if I draw that setup here, I'll start 3 tanks. And kind of show that they're all well mixed. Well mixed, that would have been a good other assumption. I'm not sure if we stated that, probably should. Of course, definitionally true for a CSTR, but still. Okay, let's have our streams coming in to the first reactor. I'll go ahead and draw that coming into the second. Draw that coming into the third and coming out. Now I'm gonna label our different variables. Sticking with concentration, I could go to molar flow rates, but I'll just do this example with concentration, just to mix things up, mostly in a helpful way. Okay, so you've got your initial concentration coming into the first reactor. So let's call this VR, 1. So this is our reactor volume 1, and we've got CI naught and V naught coming in. And because these are CSTRs and this is a liquid phase reaction, we've got the same V naught kind of everywhere. And we've got a different concentration though coming out of the reactor. So let's call, if that was CI naught over here, let's call this CI1. And that concentration coming out of the first reactor here is going to be the same coming in. So we'll have CI1 over here. Now this is VR2, but we're going to note, and I'll just do this over here on the left-hand side, that VR1 equals VR2 equals VR3. Oh, I wrote that 3 pretty big, but that's a subscript. Okay. So we have a CI2 coming out of the second reactor here. And that's what's going in to our third. And then we have CI3. Great. So changing the page now. What we want, well, before I change the page, we want our conversion target to be for this entire process. So we're going to be comparing this CI naught and the CI3. So what that means is that CB3 equals CB naught times 1 minus the conversion of B. And that's what we're going for. And you know, we have that conversion that's still the same of the 87.5%. And we knew what our CB naught was. And so when we do this calculation, we should get a CB3 of 0.01 kilomoles per meter cubed. Now, for each reactor, we have the same sort of expressions as before. I'm not going to write them all. And in fact, this is not analytically tractable. as far as I know. The reason is because you have a lot of interdependencies. But so you have this, this expression based off your design equation. And in each reactor, you also know that this is true, as we showed before. And this is basically coming from the stoichiometric table or mole balance. So, you know, you've got, between these two equations, you have two equations to solve for CB and CC. But because you have three different reactors, you're going to have to do this computationally or iteratively using trial and error. It's actually not very hard in this case. I'm not a fan usually of having to like solve things by trial and error, but you've got a lot of numbers here that constrain what your concentrations can be. You know what B starts off as, and you know what it's coming out as. So if you were to iteratively try something like assume that a third of the reaction has happened in the first reactor, well, you could plug that in and you would find out whether pretty quickly whether it needs to be more or less. And so it's not the worst, but maybe because you're working from home, you might be able to use software tools pretty readily from your computer. So if you solve this using MATLAB or using iterative trial and error, here's what you get. You get CB1 equals 0.0340 kilomole per meter cubed. You get CB2 equals 0.0175 kilomole per meter cubed. And you get CB3, well, we already know what that is, 0.01 kilomole. Go ahead and write this out, per meter cubed. So you can do your own sort of thinking about this setup in terms of what these concentrations are, what's happening. You might notice a bit of an effect of diminishing marginal returns. And that makes sense. If you think about if these reactors are all going to be the same size, and we think about a conversion of a reactor that's taking place, you know, it effectively, based on the reactor volumes and the residence time, you'd expect something like the same percentage of, or similar percentage of conversion to be happening in each reactor. And so if you're just sort of imagining this kind of process where, again, just thinking about hypotheticals, let's imagine that you have a reactor where you're pumping in 100 moles per second. I always like to use that as a round number. And you got 60% conversion. So if you have 60% conversion from 100 moles per second to begin with, you would have 40 moles per second coming out. And then if you have 60% conversion of that, well, you're consuming, I think, 24 moles per second. And so then it's 40 minus 24. You're down to 16 moles per second. And so you know right away that going from 100 to 40 is a lot further than maybe going from 40 to 16, just in terms of the raw quantity of moles per time being consumed. So that's just a reference point for why these numbers are like this. But that's not really what we're interested in here. That's just an observation. What we're interested in, I'll go to a new page, is the volume. So the corresponding residence time that you get from all of this is 2.53 kiloseconds. And then you can use that to solve for the VR. I guess I should clarify here that this is the VR for each reactor, not the total volume. And that is simply the tau times that volumetric flow rate. So that's 2.53 kiloseconds times 0.278 meters cubed per second per kilosecond. Oh, okay. Let me rewrite that. All right, that should give us 0.703 meters cubed. Okay, so that's our volume for each reactor. I'll just say VR each. Okay, then our VR total is just 3 times that. 3 times 0.703 meters cubed, giving us a grand total of 2.1 meters cubed for 3 CSTRs in series. Okay. So thanks for coming along so far. We're almost done here. We've got a couple of observations and important points to make now that we've done this calculation. So we've got a total volume of 2.1 meters cubed in the case where we had 3 CSTRs in series. Okay, so yes, there's this effect of diminishing marginal return, but if we were to compare this 3 CSTR case with 1 CSTR to achieve the same conversion, I'm going to go back. So remember, this is 2.1 meter cubed. If I go back now, before we had 6.54 meters cubed for single CSTR. So that's a lot larger. So let's think about that for a second. Well, I'll actually stay on this page here. By splitting up the reaction into 3 different reactors, even though it means that we have to build 3 reactors, we've ended up with a net smaller volume, and by a lot. Not exactly by a factor of 3, if only things were that simple, but 6.54 is approximately 3 times as much as 2.1 meters cubed. So what's more important, having smaller volume or having fewer reactors? That ends up being affected by a number of different constraints, but a lot of times you want to minimize the total amount of volume. There are a lot of costs that might scale proportional to volume. Yes, there are also costs that are involved, usually capital, for building multiple reactors, but people tend to be more willing to build multiple reactors up to a certain point, right? There's always this concept of diminishing marginal returns. Would you, for example, if 3 CSTRs make this smaller, then does that mean you'd want to do 30 or 100 little mini CSTRs just to keep making this as small as possible? Well, the good news is that you don't have to break this down into 100 or infinite smaller CSTRs. One of the major conceptual points here, so I'll write key takeaway, is that you don't have to do that. There's a type of reactor that basically achieves that, and that's the PFR. So the key takeaway is that a PFR is approximated by many CSTRs in series. Many CSTRs in series. And that's why we did this example. Because what you can see is that when you've got a well-mixed tank, and then you have an output, and then it experiences another reactor condition, and then goes into another reactor volume. Well, because in your PFR, you don't have spatial uniformity along the length. Let me just remind you what a PFR looks like. Because in the PFR, you've almost got each slice of this PFR behaving like its own little CSTR, because you continue to experience a change in concentration as you're going through the PFR. You have this continuous gradient as opposed to discrete changes. And what that means is that a PFR is usually less overall volume. And we'll talk about soon some ways to visualize that, and then we're going to go into solving some PFR problems, and then we'll also get into variable volume or variable density situations.